to show that fz equal to square root of mod xy is not analytic at the origin, although Cauchy Riemann equations are satisfied at that point. That is, even if Cauchy Riemann equations are satisfied at the origin, still fz is not differentiable at the origin. This we need to show, right? So the given function is fz equal to square root of mod of xy. Let me take this function to be equal to u plus iota v, right? And now equating the real and imaginary parts, we get u equal to square root of mod of xy and v is equal to 0 here. If v is 0, which means derivating v with respect to x gives 0 and derivating v with respect to y is also 0, right? First we are going to check whether Cauchy Riemann equations are satisfied at the origin or not. So for that, let's also find out the derivative of u with respect to x and also the derivative of u with respect to y, so that we can apply the Cauchy Riemann equations to check the result. So first we are going to find partial derivative of u with respect to x at the origin. So this is equal to limit x tends to 0 u x comma 0 minus u 0 0 divided by x. So this is equal to limit x tending to 0 u x 0, that means we have to put y equal to 0 and x as it is in u. So this is square root of mod x into 0, that is 0, minus u 0 0, putting x 0 and y both 0 in u, so that also gives 0 divided by x, so this limit is 0. Similarly, we can find partial derivative of u with respect to y at the origin. So this is equal to limit y tending to 0 u 0 comma y minus u 0 0 divided by y. So this is equal to limit y tending to 0. Now u 0 y, that is we have to put x equal to 0 and y as it is in u. So that is 0. So writing here 0 minus u 0 0 is 0 divided by y, and this is also 0. This limit is also 0. So we have got that partial derivative of u with respect to x at the origin is equal to partial derivative of u with respect to y at the origin to be equal to 0. Now what are the Cauchy Riemann equations? That is the CR equations. Partial derivative of u with respect to x is equal to partial derivative of v with respect to y. And second one, partial derivative of u with respect to y is equal to negative of partial derivative of v with respect to x. So if you notice that in the first equation, partial derivative of u with respect to x is 0 and partial derivative of v with respect to y is also 0 from here. Similarly, partial derivative of v with respect to x is 0 and partial derivative of u with respect to y is also 0. So both the Cauchy Riemann equations are satisfied at the origin. So writing this, equations 1 and 2 holds at the origin, that is the CR equations, the Cauchy Riemann equations. So we say that hence Cauchy Riemann equations are satisfied at the origin. And now we need to check the differentiability at the origin. So for that we are considering limit z tends to 0 f of z minus f0 divided by z. We need to find this, whether this limit exists or not. If this limit exists, we say that the function is differentiable at the origin, and if not, then the function is not differentiable, right? Okay, so this is limit z tends to 0. What is f of z? It is square root of mod of xy minus f0 is 0 divided by z. Taking z as x plus iota y here. So writing here x plus iota y, and this is 0. And let's take z tending to 0 along y equal to x along this line. So letting z tends to 0 along y equal to x. So this is limit square root of mod of x into y. Y is x, so writing here square divided by x plus iota y. Instead of y I am writing x, and because everything is in x, so we write x tending to 0 in place of z. So this is equal to limit x tending to 0. Now as I am having square inside the modulus, so it is positive, so writing this square root of x square divided by x plus iota x. We can take x common from the denominator, so that becomes x into 1 plus iota, right? And this is further equal to limit x tending to 0, okay, as mod of x is equal to square root of x square, right? So writing here mod x divided by x into 1 plus iota. Now since if I take limit x tending to 0 positive along the positive x-axis on mod of x divided by x into 1 plus iota, what I am getting? Along the positive x-axis, mod of x is x, right? So this is limit x tends to 0 positive, this is x divided by x into 1 plus iota. So these two cancelled out and we are getting this limit to be 1 divided by 1 plus iota. Reason, as x is strictly positive. Similarly, if we take the limit x tending to 0 negative on mod of x divided by x into 1 plus iota, so this will be limit x tends to 0 negative, mod x becomes negative x divided by x into 1 plus iota. Reason, as x is strictly negative. So these two cancelled out and we are getting this limit to be minus 1 divided by 1 plus iota, which is not same as that of this limit, right? Both the right hand limit and left hand limit are different. So therefore limit x tending to 0 mod x divided by x into 1 plus iota does not exist, which means this limit does not exist. And this is nothing but the definition for the differentiability of the function at the origin. So can we say that fz is not differentiable? Yes. So thus limit z tends to 0, if this does not exist, so limit z tends to 0, f of z minus f0 divided by z does not exist. That means therefore fz is not differentiable at the origin. At z equal to 0, and hence fz is not analytic at the origin. For the analyticity, the function should be differentiable everywhere. So fz is not analytic at the origin, even if the Cauchy Riemann equations are satisfied at the origin. Hence the result. Okay, thank you.